Welcome to Maths with AJD. We are still talking about spectral radius, and in this video, we consider harmonic and subharmonic analysis. Okay. Um, by way of introduction, we'll look at the fundamentals of harmonics first of all. And like we saw, I think in the first or second video, harmonics are integer multiples of a fundamental frequency. So you have a fundamental frequency, and then you have integer multiples of that, and what you call them will be harmonics. So if the fundamental frequency is f naught, for instance, so harmonics appear at 2 times f naught, 3 times f naught, 4 times f naught. So let's assume that the fundamental frequency is 50 hertz, for instance. Then the harmonics of 50 hertz will be 100 hertz, 150 hertz, 200 hertz, and so on and so forth. Harmonics represent periodic components in a signal, often arising from resonance, rotating machinery, or cyclic processes. So tools like Fourier transform or fast Fourier transform decompose signals into harmonic components. So FT and FFT will help to decompose whatever signal or data set we have into harmonic components, into a fundamental frequency and its multiples, in short. All right. So we have subharmonics also. So subharmonics occur at fractional multiples of a fundamental frequency, such as f naught over 2, f naught over 3, and so on and so forth. So subharmonics often signal nonlinear behavior, such as mechanical looseness, structural cracks, and chaotic oscillations. They are especially important in early fault detection, since subharmonics may appear before full harmonic signatures. So just like I gave the example the other time, if we still assume that the fundamental harmonic is 50 hertz. So it means that the subharmonics will be things like 25 hertz, 12.5, 50 over 5, 50 over 3. I think that should be 16 or number 2 over 3 hertz, and so on and so forth, So 12.5 hertz, I think that also qualifies. That'll be the fourth subharmonic, or I mean the subharmonic you get when you divide by 4. All right. So looking at the comparison now, let's look at feature and how it applies to harmonic and subharmonic. So if we talk about the fundamental frequency f naught, the harmonic will be integer multiples of of that f naught. When you talk about subharmonic are fractional multiples of the f naught. All right. So integer multiples will be things like, of course, for f naught, you have 2 f naught, 3 f naught, 4 f naught, 5 f naught, and so on and so forth. But subharmonic will be things like 1 over 2 f naught, or if you like, f naught over 2, f naught over 3, f naught over 4, f naught over 5, and so on and so forth. So what are the typical causes of harmonics? Resonance, symmetry, and periodic forcing can cause harmonics. And for subharmonics, you have nonlinearity, impacts, and faults, right? They cause subharmonics. So what are the diagnostic rules now? So when you see a harmonic or you see a subharmonic, what exactly can you learn from it? So for harmonic, it characterizes operating conditions, while subharmonic detects hidden or incipient faults, right? So let's go ahead and talk about detecting periodicity in noisy data, or if you like, noisy signal. Detecting periodicity in noisy data. Periodicity is all about, after every particular time interval, you have a particular kind of thing. Maybe after every 2 seconds, the frequency of your signal is actually 50 hertz. So after that, after 2 seconds again, you have another 50 hertz, and it goes on like that. That is periodicity. So real-world signals, especially from mechanical systems, are contaminated with noise, making periodicity detection challenging. So, and from there, let's look at things like signal processing methods. So here, we want to talk about signal processing methods in this situation. Okay. Um, so first of all, talking about signal processing methods, we have spectral analysis, and that is exactly what this topic is about. This playlist is about. So we've seen things like power spectral density (PSD), which highlights periodic frequency components even under noise, and then we have peaks, which correspond to harmonics and subharmonics. Then we have time frequency analysis, like short time Fourier transform, STFT, which tracks harmonics varying with time. And we have wavelet transform, which is excellent for detecting transient subharmonics caused by impacts or cracks. Then we have autocorrelation and Spectral analysis. So autocorrelation reinforces periodic components while suppressing random noise. On the other hand, Spectrum helps reveal hidden periodicities by analyzing echoes in the frequency domain. And then we have advanced techniques like the Hilbert transform, that is HHT, which extracts instantaneous frequency components. And we have empirical mode decomposition, EMD, which separates intrinsic oscillatory modes. And then, of course, we can use machine learning, talking about things like is it reinforced neural networks now? RNNs. And then we have CNN, convoluted neural networks. I'm not sure if that R is reinforced, by the way. Let me quickly confirm that. RNN. Okay, RNN in machine learning, yeah? So that is recurrent neural network, yes, recurrent neural network, while CNN is convoluted neural network. So in machine learning, we have advanced techniques like recurrent neural networks and convoluted neural networks, which help to detect weak periodic patterns in noisy data. So for practical considerations, right, under detecting noise periodicity, right, we can use signal processing methods like spectral analysis, time frequency analysis, autocorrelation and spectrum analysis, as well as advanced techniques. Then practical methods now, we can use filtering. We can use filtering, uh, you know, use filtering or like band pass filters to isolate expected frequency ranges. Then we can apply averaging and smoothing to enhance weak subharmonics. I think we saw the idea of averaging and smoothing when we're talking about the Welsh method and things like that. Then ensure proper sampling frequency. So the sampling frequency is really important. Like at how frequently do you take samples, or do you take a look at samples of your signal or data, right? So f of s has to be greater than or equal to 2 times f max. So that is the Nyquist theorem. We saw that in a previous video. So we have to do this to avoid aliasing, right? So let's talk about applications of vibration analysis and fault detection. So vibration analysis in rotating machinery, for instance, is the first thing we're looking at. So here we have harmonic signatures where we can have something like shaft imbalance with strong fundamental frequency components, and we have misalignment for which represent higher order harmonics. Then we have subharmonic signatures like bearing looseness, talking about subharmonic frequencies, and we have cracks in rotors, which will give half frequency components. Then we have gear defects, which can represent fractional tooth mesh frequency subharmonics. Then we have that's fault detection, vibration analysis in rotating machinery. But what about fault detection in mechanical systems? So here we have like early stage fault detection relies on subharmonic analysis. So for instance, you have a cracked shaft, there you can see subharmonic resonance before failure. And then you have gearbox fatigue, where you have subharmonics revealing irregular meshing. Then advanced condition monitoring systems integrate harmonic stroke subharmonic analysis with predictive maintenance algorithms. So those are fault detection techniques in mechanical systems. Then we have broader applications of these things like in aerospace for detecting fatigue cracks in turbines and propellers. And in civil engineering, we can identify nonlinear vibrations in bridges or towers. Then for medical diagnostics, we can have we can analyze subharmonics in heart rate variability or vocal cord vibrations. So talking about systematic workflow now. So if you want to talk about systematic workflow for harmonic and subharmonic analysis, so first of all, you want to acquire a signal. So you talk about signal acquisition. So you want high quality sensors, accelerometers and microphones to get your signal. And then you need proper sampling to avoid aliasing, right? You want sampling frequency greater than or equal to 2 times f max. That's, I think, 2 times the harmonic frequency, the fundamental frequency, I want to believe. Then we have pre-processing. After you acquire a signal, right, you pre-process So in preprocessing, you have to do noise filtering. You can talking about low pass or band pass, and then you can talk about normalization of amplitude. So I think in the previous video we had talked about data preprocessing in the time domain. So some of these things look like that a bit. Then we have frequency decomposition. So you can use fast Fourier transform for harmonics, while you use wavelet and EMD for subharmonics. And then we can go ahead and talk about feature extraction, which identify peaks at multiples of f naught. That's the harmonics now. Integer multiples of f naught. We talked about harmonics, and then we have fractional. We have the fundamental harmonic, the fundamental frequency divided by n. Talking about the subharmonics. Then you can calculate relative energy and persistence over time. Then, of course, we can then go ahead to fault diagnosis, where we map frequency features to fault types like imbalance, crack, and misalignment. Then we can use thresholds or machine learning classifiers. Then we can also have decision support, where we predict remaining useful life of a machine, for instance, or we can have trigger alarms for maintenance. So once a particular kind of thing is going on in the machinery, you can have a trigger to say, oh, something needs to be fixed or something needs to be changed. In summary, we have that harmonics describe standard periodic responses, while subharmonics reveal hidden non-linear faults, right? So, and then we have detecting periodicity in noisy environments requires advanced signal processing like Fourier, Wavelet, Hilbert or machine learning. And we see that applications of vibration analysis and fault detection are crucial for early diagnosis of machinery issues, improving safety and reducing downtime. So all the stories you've told so far, can we talk about some Python implementation of this thing? So the first thing, we are doing some imports and helpers. So we import the necessary libraries like NumPy for array computing. We have PyPlot for Matplotlib rather for data visualization. We have SciPy where we can get signal. And from SciPy signal, we have things like find peaks and Hilbert. So for instance, if you want to find peaks, and then for NumPy, you also get fast Fourier transform where you can get RFFT and RFFT FREC. And then of course, those are the imports now. For the helpers now, so you need to define, so of course we do np.random67, and that's to ensure that each time we run the code, we always get the same rate. And then subsequently, you define a set of functions that does some jobs for you. Like you define a function called db10 taking value x. So an x is, and so this is like an initialization. And then when that happens, you now you now return 10 times log to base 10 of x. So like that. So, and you have 1 e raised power minus 20. Then you define another function that's next power 2n. So in that case, now you have integer 2 raised power the ceiling of log 2 base log n base 2, I want to believe. All right. Then you also have annotate peaks. You have this code going on. Don't forget to run it. Of course, you won't get a result from this one first because it is just a preparation for other things we have to do in the process of this. Okay, so the next thing is you want to simulate a vibration-like signal with harmonics and subharmonics. So we construct fundamental frequency to be 25 hertz, while harmonics will be things like 2 times f naught, that's 25, 3 times f naught, that's 75, and then we can have subharmonics like f naught divided by 2, which is common in looseness or cracks. So f naught over 2 will be 12.5 hertz, for instance. Then we can have intermittent impacts like bearing, like which talks about things like broadband plus envelope periodicity. Then we can have additive white Gaussian noise. So talking about the sampling now, so if you take 2000, if we have sampling frequency of 2000 and we have a duration of 5 seconds, right? So, and then we can set up, so based on the fundamental thing we had done before, and then we can go ahead and declare Fs is 2000, just like what we see now. T, that's the period, is 5.0, as we've seen already. So the time will now be 0 to t, and then it will be, we have 1 over fs divisions. That's 1 over 2000 divisions of this 0 to 5, right? And then we have fundamental frequency is 25 hertz, just like we saw there. Then the harmonics are 2 times f naught, and you take that as 0.35, and you have 3 times f naught, you have 0.220. And then for subharmonics, you have f naught over 2. Of course, you take that again, 0.25. All right. So from there now, we can then declare our signal, which is x equals 0.9 n pi sine 2 pi ft, f naught t like that. And then we say for f and a in harmonics, we declare that signal, that's 2 pi ft plus 2 pi. So we have a random thing that's adding noise there now. Then we have lines 11 and 12 for harmonics and lines 13 and 14 for subharmonics. Then we uh, add impact every one over f impact cycles with jitter. So you have f impact, that's 12.5. Envelope rate, e.g. ball pass frequency. Then you can generate impact times first, then add jitter with the same shape. So base impact times, you declare that here. Impact times, you also declare that as base impact time plus 0.04 plus, that randomness, some kind of noise, I want to believe. So from there, so we have the impact signal. So you have np dot zeros underscore like t. Then for it in impact times, you do all this. You can take time to look at the codes a bit more intently, right? So we also have some additive noise. So at the end of the day, we run this and we can get a plot out of this. So we have this plot now. So you can see it's all so smooth. So this is simulated time signal, and after the first is 1 second and all that. Okay, so from here now we can go ahead and talk about the fast Fourier transform and power spectral density using Welsh this time around. So you use Welsh power spectral density to stabilize estimates under noise. So identify peaks and compare to F naught multiples and fractions. So for the Welsh now, you have number per segment 4096. What Welsh does is that you take portions of your signal, and then you have some overlaps in between. So here we have number per segment, that's 4096, and number of overlaps, you divide that by 2, modulo division by 2. Of course, that's just going to be that'll be 2048. And then you now plot the periodogram against the frequency like that using the Welsh thing. And then, of course, you can look at this a bit better. And then we run that and we get something like this. So here we're able to detect some peaks, right? So Welsh PSD with detected peaks. So we detect the first peak around 12.70 hertz. Then the second one is around 24.90, and it just goes on like that. So then we can go ahead and estimate fundamental frequency f naught in two ways. So we can use autocorrelation, which tells us that autocorrelation peak lag, which implies that f naught is approximately f of s over maximum lag. And then we can also go spectral, where we see that spectral, you pick the largest low frequency peak where you exclude DC, and we combine both with a sanity check. And that's exactly what we're doing next. So we talk about the fundamental estimation. So for the autocorrelation part, you have x sub d equals x noisy minus the mean of the noise. All right, that's some kind of clean. So removing the DC is removing the average of the noise, right? And then you have ACF. That's the autocorrelation function for sure, right? Since we're talking about autocorrelation, so you have ACF, signal correlates XD mode full, then you have ACF again, giving you that. Then you have the lags, that's the length of the ACF. So you ignore very small lags where you exclude DC neighborhood. So minimum lag is integer 0.02 times fs. So you ignore anything less than 20 ms. And lag max, you have 0 to fs, such up to 200 ms. That's 5 to 50 hertz band for this frequency. Then lag peak will now be lag minimum plus np dot ag max and all of that story. Then you have f naught underscore ACF. You have fs over lag peak. This is where you get the f naught now. Then using the spectral method, you can choose the strongest peak between 5 to 80 hertz. So you mask, and that is f underscore PSD greater than 5, all right, and f underscore PSD less than 80. So we have candidates cand underscore idx np argument and all of this, right? So you can take a bit of time to look at this whole thing. So from here now, we run this, and we have we're able to detect. So for the first, so you can get something for the first 0.5 second lag. So f naught ACF is 12.5, f naught spec is 24.90, f naught underscore EST is 18.70, and so on and so forth. So we have that for the autocorrelation. So we can classify peaks as harmonics or subharmonics. So we can classify peaks as harmonics or subharmonics. So for each detected spectral peak at frequency fk, so if the absolute value of fk over f naught minus n less than epsilon is giving us the harmonic, talking about integer n, and you have so if the absolute value of fk over f naught minus n is less than epsilon, that's harmonic, right? Meaning that that's integer n. Then in this case, if absolute value of fk over f naught minus 1 over m, that absolute is less than epsilon, then you talk about subharmonic, talking about integer m now. So this is classifying harmonics and subharmonics based on the peak frequency, the spectral peak at frequency fk. So we print label tables and highlights on PSD. So here now, see what we have. Okay, I mean, I can expand it and then just go step by step. I just want to make sure. Okay, well, when we get there, we'll look at all those things. So classified peaks, now you have f naught underscore est equals float of f naught underscore est and ratio f underscore psd of peaks slash f naught underscore est. So EPS is 0.05. That's 5% tolerance. That's epsilon. The epsilon we saw up here, this epsilon now is 0.05. So usually in mathematics, epsilon is a very small number that is positive, it's not negative, but it can be very small, like maybe 1 over 1,000, like here 95 over 100. So in other places it can be like 1 over 1,000 or 5 over 1 million, something like that. But it's very small number, but positive. Then you initialize with labels, and then you say for R in enumerate ratio, then you have in nearest integer for harmonics. You do that. N is integer np dot round R. The nearest reciprocal integer for subharmonics. So you have M, which is np dot round 1 over R now instead of the R directly. So subharmonics will now be fractional, as we know already. So the kind is all that tag. If n is greater than or equal to this, and absolute this is all that. So you do all these things. So you can take a bit of time to look at this. Right now, I just want to run it. So of course, the code can be better looked at. So we have all this. We have the frequency, we have the PSD, we have the type, whether it is subharmonic or other, whether it is harmonic. So for the first one, we have the frequency is 1.95 and the PSD is minus 29.46. That's the power spectral density is minus 29.46. The type is subharmonic, all right, and then the tag is 1 over 10, and then the f of over f naught is 0.104, like that. Okay, so then all these other ones are order. Then we have at 75.20 frequency, we have the power spectral density to be minus 16.33, and it's harmonic because n is equal to 4 and f over f naught is 4.021, like that. So that's what we get from that. What we have actually done there, like I said, is to classify peaks as harmonics or subharmonics. So we can do that kind of classification. Okay, so next we'll talk about time frequency view, using STFT. So you can use STFT to verify stability or appearance of components over time. All right, so we have parameters. We talked about window length, which is approximately 0.5 seconds, and it's overlapping at 50%. So here now we have STFT spectrogram. Number per segment is integer 0.5 times whatever the frequency, sampling frequency is. I think it was 2000 when we started out the other time. Number of overlaps, that's the whole number, the integer division, that's divided by 2, whatever you get. The decimal part, we don't care. All right, so and then we have F of the frequency attached to STFT, the time, and SXS. That I think this is the, I think this is the spectral density or something like that now. Yeah, so we can run this. That's the spectrogram. Yeah, PXX is periodogram. This is spectrogram, and this is what we get when we plot that, right? Okay, so we move on to wavelet for transient and subharmonic detection. So we use wavelet we can use wavelet to detect transient. We can do transient or subharmonic detection using wavelet. That's what I mean. So we use the Mollet wavelet with SciPy or signal.cwt. I mean, but in trying to run this, I had a lot of trouble with this. So I had to go a very long way to do this, like another way entirely. So here you can have scale to frequency mapping to approximate for Mollet, and F is approximately Fs over scale.k, where k depends on wavelet parameter. Okay, so I mean, you can see the code is pretty long. So I won't even bother trying to go through it. I'll just run it. But of course, you may want to consider it later. It's a whole lot, and it probably doesn't have anything to do with the previous thing we've been doing, because we now have to go the way of trying to do some backend stuff, doing some defining functions and using all kinds of if statements and things like that. Normally, we should have been able to get that from that SciPython, and wouldn't have had to deal with this plenty code, so to speak. So we should have been able to get it from SciPy or Signal, but I think there's a deprecation issue that maybe it used to be there before, but it's no longer there. I suspect that's the deal. So you can even see the code is taking a long time to run. So let's see what it gives us when it's done running. Okay, so we finally get this. So here we have CWT for midband focus. All right. And then we go ahead to Spectrum. This is new. Spectrum to review periodicity. That's echoes in the spectrum, right? So we want to find echoes in the spectrum. So this compute the real Spectrum to detect periodic spacings in the spectrum. So Spectrum helps us to see echoes in the spectrum to reveal periodicity, that is. So a peak at frequency Q at a peak at Q frequency Q cap implies a periodic spacing del F, which is approximately 1 over Q bar in the spectrum, often tied to the fundamental or envelope rates. So for the real spectrum, now you now have n next power. I think we defined next power somewhere before now. Yes, that we defined next power I think in the very first place where we did the helpers and imports, right? So, and we are calling the next underscore POW2 function now. And then we are running this with the argument length of noisy signal, right? And then we have X to be np.fft.rfft and all of that. Then we have log underscore mag, we have sep. So this is the spectrum itself, sepstrum. Sepstrum, this is the sepstrum in line 6. All right. So it is we take the np.fft.irfft of the log mag that we have right here. And then we have every other thing like that. I'll just go ahead and run this so you can look at the code better. So this is the kind of thing this gives us. So we have the Cepstrum based fundamental to be about 12.90 hertz, right? So we have the Q frequency in this case, like that. So we can also talk about the envelope analysis bearing like impacts now. So we can have bandpass around the structural or high frequency resonance, e.g. 200 to 600 hertz. We can have the Hilbert envelope, all right, to reveal modulation at impact rate, e.g. ball pass frequency. And then we can have the power spectral density of the envelope. The PSD of the envelope should show a peak near the impact repetition rate, which is approximately 12.5 hertz here. Okay. So again, we want to do the envelope analysis workflow. So first we declare all the band pass, high band pass, low band pass, 200 to 600 SOS, that's signal. So we have the signal, but to be all that, we have X underscore BP, then we have the analytic, which is Hilbert, we have the envelope, which is absolute value of the analytic. We do the PSD of the envelope, low rate content. So we do the PSD against frequency like that. And we have PF underscore PSD still here. All right. So that's dB10 of PEMV. And then we do the plots. We do all the plots. So first plot is about band signal, low, high, and all that. Second is about Hilbert envelope, first 1 second. Next is about envelope PSD, that's envelope power spectrum density. So if you run that, you have all these things. So this is the first one, band pass signal between 200 to 600 hertz. Then the next you have Hilbert envelope. This is what that looks like. For the envelope PSD, then we have some peaks detected like that. Then we can talk about simple fault detection, simple fault indicator features. All right. So yeah, you can compute interpretable indicators often used in condition monitoring. So for instance, you have spectral, you have amplitudes at F0, 2F0, 3F0, F0 over 2. So here you have envelope rate peak near expected impact frequency, F impact. Then for the statistical, you have RMS, kurtosis, or impulsiveness. This form a lightweight held vector for thresholding or machine learning. So for feature extraction. And we talked about the workflow the other time, and now we're talking about feature extraction where we actually indicate which is where it indicates about the sub-harmonic or harmonic, right? So let's see. So in this case now we're talking about some features of the signal. So we run this now, and then we see the RMS is 0.93. That's root mean squared. You have the kurtosis, which is statistical thing about is it right-tailed or left-tailed kind of distribution. Then you have the A times fundamental frequency, 2F naught. So you have the A of fundamental frequency. I think that should be the amplitude. And so you have for the fundamental frequency, you have for the second harmonic, or 2F naught, and you have for the 3F naught like that, and you have the subharmonic also, and envelope EMV at underscore ARB underscore at underscore FIMP, you have 5.33 like that times 10 for -5. So let's talk about some minimal rule-based flags. So for toy, let's use a toy logic for illustration. So if envelope rate energy at F impact is high and kurtosis is high, we have impact present. Then if subharmonic band energy at F naught over 2 is strong relative to F naught, we have possible looseness or crack. Then we can then tune thresholds using healthy or faulty data sets. So in this case now we have some simple flags for toy threshold. So we have a flag. So you have flags of impact present. So you have the features EMV underscore at FIMP greater than 1 raised by -5 and features of kurtosis greater than 3.5. Then you have flag subatomic alert equals features, all that. And then you have then you print like that. You see impact present for this one is false. For subharmonic alert, it's true. So we are trying to get some simple flags in that case. So some things you can note and next steps. So we can calibrate thresholds from real data, like healthy versus faulty baselines. We can consider other tracking for variable speed machinery. We can have robust subharmonic detection, expand the rational grid, e.g. P over Q with small integers, and perform model selection, say AIC or BIC. AIC, I think, is Akaike, Akaike something criteria. I've forgotten what that I is. Then we have ML pipelines. We have ML pipelines, which we use. So use features above plus cross validation for classification and regression. So that can help to detect the remaining useful life. In summary, we have seen that fast Fourier transform slash power spectral density identifies spectral leaks, and we can have classification with respect to fundamental frequency F naught, which separates harmonics versus subharmonics. All right. So these fundamental frequencies, of course, since once you have that to the right, you have the multiples, which are subharmonics, and to the left, you have subharmonics, which are divisions, which are fractions of the fundamental frequency. So we have autocorrelation and Spectral, which estimates F naught under noise and reveal periodicity. So you want to cut through the noise to find out what the fundamental frequency is for in a noisy signal or data. Then you have short time Fourier transform, which shows time localized behavior, and CWT highlights, and that's a wavelet thing now. So CWT highlights transient stroke subharmonic content. Then we have envelope analysis, which exposes impact repetition rates typical of bearing faults, and a simple feature set such as RMS, kurtosis, and band energies and envelope rates supports rule-based or ML fault detection. All right. So with this, we come to the end of this video about harmonic and subharmonic analysis. All right. Let me know how helpful this video is for you. And if you'd like me to try something, feel free to let me know. If you have subscribed already, thank you so much. If you haven't subscribed, of course, you know you're missing a lot. So you want to go ahead and subscribe. After subscribing, you want to hit the notification bell so you can always get alerted each time a new video is released. After then you can take it a step higher. You can click on join and become a member of the channel. That way you can have some some very special privileges like that. Ultimately, don't forget to comment, like, and share so that you can always so that other people can have access to this great content I have going on here. Till I come your way again, keep doing maths right, keep doing data right, keep doing Python right, keep doing everything right. Bye.